More than 5 billion years ago, a star exploded in a fiery supernova, and our solar system was born. That initial explosion was massive. It spewed an almost unimaginable amount of wreckage into a nearby cloud of hydrogen gas and interstellar dust. The cosmic debris began to spin, and at the center, a new star, our Sun, began to form. All around that nascent sun, the matter in the swirling disk also began to collide and clump together. Bits of iron, silicon, magnesium, aluminum, and oxygen met and combined. Over millions of years, the collisions produced larger and larger bodies in space. The larger they grew, the harder they hit. As they collided, they exploded, and their components began to separate and sort themselves out. As dense iron settled in the center, and lighter rock separated into a mantle around the iron core, the planets we know and recognize today began to take shape. Then suddenly the sun ignited. The force of that explosion blew away the hydrogen gas in the cloud, and only the planets remained. At that point, the Earth was an ocean of red-hot molten rock. As the collisions slowed down, our planets began to cool, its surface crusted over, but inside its core, the molten magma continued to boil and bubble. Periodically, water vapor broke through the crust and condensed in the Earth's atmosphere. Clouds formed, rain fell and fed oceans, and crystals formed. In fact, when you hold a crystal in your hand, you could very well be holding an object as old as the universe itself. Many people are attracted to crystals simply because they're so old. That fact makes them fascinating to contemplate. They were here eons before humankind, and they will last far longer than any one of us. In fact, the oldest rocks found on Earth are almost 4 billion years old. The Earth itself might be considered a giant rock. Its center, as you probably learned in grade school, is surrounded by pure liquid rock, molten magma, 1,860 miles thick. Most crystals spring from the center of the Earth. The Earth's center is surrounded by a crust of massive plates that range from 3 miles to 25 miles thick. Most of the crust is covered by ocean water, while we live on massive continental islands of granite floating on the mantle of the Earth. In the process, some areas of the world erupt in volcanoes, while other areas tremble their way through earthquakes. Some parts of the Earth are thrust down back toward the core, while others rise up in the form of mountain ranges and vast plains of lava. As the Earth's crust shifts, it fractures, creating fissures and cavities. Chemical-rich fluids flow through the newly created spaces, and suddenly all of the ingredients of crystal creation are in place. Chemical components trapped under high pressure with time to grow. Crystals form when chemicals, heat, pressure, time, and space combine in just the right measure. Crystals are seeded when liquids cool or freeze into solids, when dissolved matter precipitates out of a solution, or gases condense. Exactly what types of crystals will form depends on the chemical mix in play, as well as the time, temperature, and pressure involved. Some crystals like diamonds, emeralds, and rubies form within the Earth as molten rock cools slowly over long periods of time. Some crystals grow inside gas bubbles after magma has reached the surface. Others form as water and other liquids evaporate. However, simply having molten rock available is no guarantee that crystals will form. If molten rock cools too quickly, as when lava is injected from a volcano, there won't be time for crystals to take shape. And if some of the conditions aren't just right, some chemical elements will simply cool into aggregates of smaller interlocking crystals. So as the Earth's crust shifts, crystals can break. New elements can be introduced into the mix, which can affect a crystal's chemical makeup, color, and growth patterns. Sometimes chemical impurities can crystallize inside a host, or cavities of gas can be incorporated within a crystal. Ultimately, there are 3 ways that crystals can be created. Igneous rocks and crystals form deep within the Earth. When red-hot magma cools, it could cool beneath the surface of the Earth, or it could erupt in a volcano and cool on the surface. Igneous rocks that cooled slowly are usually comprised of large grains of minerals because each grain had more time to grow. Igneous rocks that cool quickly are finer and look more delicate. Metamorphic rocks and crystals form when the Earth buckles and shifts, which puts some crystals under intense pressure or high temperatures. Some crystals melt when they're exposed to heat, or when they come into direct contact with hot magma that has forced its way into cracks and fissures. Some minerals can also be transformed into other minerals without melting first. They may undergo a chemical shift as a result of heat and pressure, or they could come into contact with chemical solutions that migrate through the rocks. They might even be forced to combine with other minerals by being squeezed into the same place at the same time. Sedimentary rocks and crystals form as minerals crystallize from layers of sediment in low-temperature solutions. That sediment generally comes from igneous rocks worn away by rivers and streams. Bit by bit, piece by piece, flowing water carries those rocks and crystals away and washes them into lakes, oceans, or seas. Over time, those fragments are laid down in layers where they harden into rock. This cycle can be repetitive. Sedimentary rocks can be transformed into metamorphic rocks, or they can be shaken loose during earthquakes, tumble back to where the Earth's core, and melt once more into magma. From cooling magma, crystals form. With time and heat and pressure, they undergo metamorphosis. Once exposed to the elements, they can tumble free or be worn and washed away into sedimentary deposits, where once again they can find themselves reborn in the center of the earth.